Great moments are born from great opportunities. At the UCL Rover team, we have been working tirelessly since last September to seize the opportunity to compete in the University Rover Challenge. We have pushed the limits of our knowledge to create the first ever Mars rover in the history of UCL.
The suspension of the rover consists of a modified rocker bogie mechanism, with two shock absorbers integrated within a differential bar to minimize the dynamic loads we expect to face in the URC competition tasks. The chassis has been designed in two sections, with the front end designed to accommodate the robotic arm and a rear bay to house all electronics and hardware in a safe and protective environment.
For the power and drive system, we are using 6 lithium polymer batteries delivering power to 6 brushless DC motors. The high current supplied will be perfect for our rover during the competition when faced with rough terrains. For the control system, we developed an in-house channel switching technique which allows us to control the multiple subsystems with minimal disruptions. Multiple microcontrollers are used to ensure the effectiveness of the system and of the entire rover.
Autonomous system uses robotic operating system with GPS navigation, obstacle avoidance, and tennis ball detection functions. Firstly, we obtain the current and desired GPS coordinates from GPS interface and send them to the rover. Once the rover has received these coordinates, it will know its location and navigate itself to the desired location. Along the way of traveling to the desired location, the rover will avoid obstacles through algorithms such as SLAM and common filter collected from depth camera. We have offset the light of depth camera to black and white because the strong sunlight in the competition creates many noise. Once the rover arrives at the desired location, it will turn around until it detects the tennis ball through cafe library and drives towards to it until it stops at a safe distance.
Our arm has 5 degrees of freedom with the load-bearing joints being controlled by worm gears and stepper motors. We chose stepper motors for 4 out of 5 joints coupled with a worm drive system as they provide good holding position and high gearing ratio. Inverse kinematics models have been embedded into the control system to precisely point the end effector to the desired location. Durability of joints and links have been checked, using finite element analysis, and gears have been specially designed to withstand the loads. The arm can easily be deassembled when not needed to lighten the rover and make it more modular.
In terms of science hashtags, the aims for these tasks are to determine the potential of sustaining microbial life, geology of the site, and microbes life detection. These are done by rover science testing and laboratory tests. Our rover science testing involves the use of temperature and soil moisture sensors that will be attached to the drill, and microscopic images to determine the soil structure qualitatively. Our site selection criteria is mud, cracks, or surfaces with the least number of rocks and evidence of past water activity. Meanwhile, our lab tests consist of soil pH test, elemental chemical test, and lipid emulsion test as our plant biological life detection assay.
The science module will be attached onto a special housing which holds both the drill and the sensors. We will be using an auger to collect the sample, which will be held in a carbon fiber container before getting transferred into the airtight containers on board the rover for further testing. The housing will then switch to the sensor module to be inserted into the hole dug earlier to gather the respective data from the sensors for analysis.